All right, I'll jump in with a little bit of introduction. For those who don't know me, my name is Eric Sperling at Stanford University, and this Proxy Primer series today is brought to you or organized on behalf of the SGP, or Sedimentary Geochemistry and Paleoenvironments Project, which you can just read from the screen, is a community-oriented research consortium aiming to both aggregate and then analyze sedimentary geochemical data through Earth history. And if you're not involved, we all hope you will become involved. Please check out our informational website at sgp.stanford.edu or our phase 1 data product, which is available on our search website. We would love to have you involved. So we started this Proxy Primer series because it was clear that there was an appetite among a lot of people, especially people that weren't primarily geochemists, people like geologists or stratigraphers or paleontologists, to understand some of the details of the various proxy systems and geochemical methods that we use to understand the environmental record on Earth. And so the goal is to create this lecture series and ultimately a YouTube series that will be available for people looking to learn more about these proxies, starting at a relatively accessible level, and then also provide an open space for interaction with experts on these proxies. And so once...
I'm gonna turn on the scale before I dump the beans in.
Sorry, we have someone with their sound on, I think, still. Yeah, and so after the lecture, we'll turn off the recording and we'll all be able to ask Alan questions. So we're lucky enough today to have Dr. Alan Rooney from Yale University giving this lecture on rhenium-osmium geochronology and osmium isotopes. For those of you who work in the Neoproterozoic, you'll be really familiar with Dr. Rooney's work. For those of you who aren't, the big problem in understanding the Neoproterozoic, or one of the big problems, has always been the lack of absolute age control. And as Sam Bowering always used to tell us, no dates, no rates. If we don't have these absolute ages, we can't correlate and we can't tell anything about what's going on in their system. And so to me, at least, some of the most important advances in understanding the Neoproterozoic in the last few years, things like understanding the synchronicity of the Snowball glaciations, or the age of the Shuram excursion, or the age of the vase-shaped microfossil assemblages, have all come through the work of the rhenium-osmium geochronometer, as applied by Dr. Rooney and his lab. Rhenium-osmium can also tell us a lot of other things, though, as we'll hopefully learn about today, things about weathering processes and ice sheet dynamics, those sorts of things. So it really is a really powerful system. On the other hand, many of us aren't as familiar with it as something like uranium-lead geochronology. So it's great to have the opportunity to learn about this system from Dr. Rooney. Just as a little bit of his personal background before we jump into the lecture. Alan's from Scotland originally. He did his undergrad at the University of Glasgow before moving on to Stockholm for a master's and ultimately Durham for his PhD. He then went to Harvard University, where he continued working on the Neoproterozoic for his postdoc, and started as an assistant professor at Yale University in 2017. So Alan, thank you very much, and we look forward to the lecture.
Sure. Thank you, Eric, for a really nice introduction, and thanks everybody for turning up at whatever time zone you're on. I will try to share screen, which after a year and a half or more of Zoom, I'm still intermittently successful with. All right, let's go. Let's try PDF. Can you folks, hopefully, can you folks still see this? No, there we go.
Yes.
Oh, sorry, faked out. All right, hopefully you can see this.
Yeah.
Thank you. I'm gonna shift this out of the way so I can see what's coming up. And yeah, so thanks, Eric, for the invitation and the opportunity. And yeah, everybody for coming along. And as I understand, there's going to be a question section after the lecture, but please feel free to interrupt and ask any clarifying questions or sort of highlight any dropout or issues. So today I'm going to introduce, for those of you that are not familiar, the rhenium-osmium geochronometer as it's employed in sedimentary rocks. And also touch a little bit on the use of osmium isotopes as a paleoweathering proxy and the opportunity to sort of use that system to sort of deconvolve a number of issues that we as geochemists, geologists, and geochronologists and paleontologists all sort of work with on a regular basis. So the flow of today, I'm going to try and go from rock to data and show folks, how we do what we do in the lab, as well as how we interact with you folks in your own subdisciplines, and how we can sort of improve and move on in calibrating Earth history. So I think that's right. So yeah, as a geochronologist, I'm really interested in calibrating Earth history and refining what you folks are looking at right now, which we're all very familiar with, this geological time scale. It's an old version here, but you can see the sort of 4 panels that make up the 4.56 billion years of Earth history. And we're very familiar with the Cenozoic, Mesozoic, and Paleozoic, and the time scale there. During our undergrads, we all learn how to tell time. But this quarter panel over here, which is sort of lesser known, I think. This is what I'm really focused on, or have been focused on for the last sort of 10 or so years as a geochronologist. And one of the main differences here is that in the Precambrian, as is labeled here, we have minimal biostratigraphy, that is the ability to tell time using paleontology. Despite the fact that the Precambrian, as you can see, makes up 88% of Earth history. And so this is where geochronology really comes to the fore in telling time in this component of Earth history, which hopefully I can illustrate today is a really fascinating part of Earth history, arguably one of the most interesting. Okay, so outline for today, the time that I've got with you folks, I'm going to introduce the Rooney-Osmium system, the decay system, and the geochemistry of these two transition metals. And then I'm going to talk a little bit about sampling, how I sample, how my lab group sample, and how I would ask you folks to sample in the future for this system. And then talk a lot about the chemistry involved in generating Rooney-Osmium isotope data. Touch on the mass spectrometry and the data reduction. And then from that foundation, build up onto some applications that I'm familiar with and some things that I'm starting to get interested in. And then touch a little bit on future work that myself and other Rooney-Osmium geochronologists are working on in order to improve the system. So this is where we'll be going for today. Okay, so as Earth scientists, how do we tell time? One of the most sort of well-known systems, as Eric mentioned, is the uranium-lead system, which in zircon is producing eruptive ages for zircon, and it's incredibly high precision, 0.05% and even better in some cases. And it's known as the gold standard for geochronology. And then, of course, there are other systems, the argon-argon system and many others. But uranium-lead is what I think we best know and most trust. It's most reliable, and it's the most accurate and precise. But it requires zircon, the presence of zircon, eruptive magmatic zircon. So if we're in a situation where we don't have zircon, how can we tell time? And obviously, biostratigraphy in large parts of Earth history is an incredibly powerful tool. But if we are pre-biostratigraphy, then the other technique that I'm going to try and advocate for today and encourage folks to sort of think about is the Rooney-Osmium system, in which case we can use this system to generate depositional ages for the sedimentary rocks, and also use the osmium isotopes as a chemostratigraphic tool, similar in the way that, for example, strontium has been used. All right, so that's the sort of motivation for what I do and sort of the opportunities that Rooney-Osmium can provide. I want to provide a little bit of background for the Rooney-Osmium system. For those of you that are not familiar with these transition metals, they're both very compatible elements. Rhenium is slightly more incompatible than osmium, and so they're found predominantly in the mantle and in the core. They're highly siderophile elements, so they'll bond with iron alloys, as well as being chalcophilic, so they'll iron and sulfur. So metal and sulfur are the sort of compounds in which these two metals most predominantly go into. Upon mantle melting, so once we melt the mantle and produce our basalts, rhenium, as I said, is more incompatible, so it'll go into the melt is a sort of different partition coefficient, so it will go into the melt more readily than osmium and gets extracted out as we produce continental crust. Upper continental crust, rhenium has an abundance of around 100 to 300 picograms per gram, osmium around 50 picograms per gram. So osmium is actually the second rarest element in the Earth's crust. Rhenium is moderately, very slightly more concentrated in the Earth's crust. And yeah, so this is a chart from one of James Day's paper in 2013 showing you a range of materials and their osmium concentrations and rhenium concentrations. And so these are predominantly periddotites, morbs, OIBs, continental basalts, and so on and so forth. And you can see that they have a large range in osmium elemental abundance, or fairly low rhenium abundance. In contrast that with the blue shapes up here, where we see black shales or sedimentary rocks, where there's a massive enrichment in rhenium over osmium, and that's related to do with this varying partition coefficient and compatibility. And then if we look at this a little bit in isotope space, and don't worry about the details, we can talk about this at length. You can see that the rhenium-osmium ratios of black shales, again, are really high in contrast with our periddotites or komatiites or morb. And then in osmium isotope space, black shales or sedimentary rocks are really radiogenic, and that's due to this ingrowth of radiogenic osmium through beta decay of rhenium. And so this is a sort of the communities that exist within the rhenium-osmium geochemical community, is that we have a mantle community where we're looking at the evolution of continental crust and planetary differentiation, and then there's the sedimentary rock geochemistry group where we're looking at geochronology using sedimentary rocks. All right, so these two elements, rhenium has two naturally occurring isotopes, 185 and 187. Osmium has 7 naturally occurring isotopes, 184 through to 192. We have a decay system in here. 187 rhenium decays to 187 osmium through beta decay with a half-life of about 42 billion years. And so we can leverage this system to date sedimentary rocks across large portions of Earth history. All right, and then, yeah, sort of a nod to the evolution in the timeline of rhenium-osmium as a sedimentary rock geochronometry system. Greg Ravitz and Carl Trikian published this in 1989, where they were looking at the Bakken Shale producing a rhenium-osmium sedimentary rock age of 354 million years, in agreement with the understood age at that time. And so this was the first time one of the first times that this system appeared within the geosciences as a potential chronometer for understanding the evolution of continental lithologies. Right, so diving into the geochemistry of rhenium-osmium, they're in crustal rocks and they're being weathered and they're undergoing the processes that we see today. Under oxidative weathering, rhenium and osmium are weathered out of rocks and transported through riverine flux into the oceans. And in oxic waters, rhenium and osmium are both soluble and where they can be complexed by organic matter. And so this is it's a really neat study where they looked at macroalgae or seaweed from the northeast of England, where they were collected, and they cut up different parts of this macroalgae, did elemental and isotopic analyses on it, and you can see this range in both isotopic composition and elemental abundances within this macroalgae. So this is in the photic zone on the holdfast it's growing, and it's incorporating rhenium and osmium. So in addition to being siderophilic and chalcophilic, rhenium and osmium are also organophilic, although I would mention that there is no biological use for either element. There's an incorporation, but there doesn't seem to be any biological effect or any biological need, certainly within the macroalgae. And so putting this into context, putting this range in rhenium and osmium enrichments, the seawater which this seaweed was retrieved from, the osmium elemental abundance of that seawater is 0.01 part per trillion. The rhenium elemental abundance was 0.08 parts per billion. And so you can see, in contrast, the blades, the tips, all the parts of this macroalgae is massively enriched in the both rhenium and osmium. You can see the rhenium-osmium ratios of, there's a range of about 25,000 from 30,000 here, 4,000 here, and so on and so forth. The site at which this was collected, osmium isotopic composition of seawater is 0.91, which is in pretty good agreement with large parts, a number of parts of this piece of seaweed, especially the holdfast and the vesicles and stipe. So this is how we understand that rhenium and osmium are being complexed into organic matter. And then, so once it's in the organic matter, and that organic matter then passes down through the water column into a suboxic or disoxic or anoxic setting, the rhenium and osmium that's complexed into the organic matter then goes into the sediment pile, becomes lithified, and you have a closed system. And that's one of the prerequisites for the isotopic system we're looking at today, is that it's experienced closed system behavior throughout its history. All right, so sampling. So how do we go about sampling for rhenium osmium geochronology? So there's sort of two approaches. We can be doing fieldwork, and so outcrop sampling, and we also employ using drill core sampling. And so I'll give some pros and cons for each of these, and some sort of outlines on how the approach is done. It's how we get our rocks. We sample them in the site and then take them back to the field. Okay, so outcrop sampling, we're not sample limited in general. And we also, the great bonus is that we have stratigraphic and paleontological and sometimes geochemical context for where our samples come from. We can have proper stratigraphic frameworks for where our samples come from. So the procedure is to collect a series of samples, a series of hand samples along strike, so along a bed, over several meters, even tens of meters if possible. And we want to do it over a short vertical interval, which I'll hopefully emphasize why that is. That's so that we're getting an osmium isotopic composition for each sample that is identical or comparable. And the lithology that we're looking for is something that's competent, very fine grained, but we don't want something that's fissile. And so you often hear black shale geochronology and so on and so forth, and that can be a little bit of a misnomer because the facility of said lithologies is actually a hindrance. So anything that has weathering planes is a real problem for us. We want to avoid veining or any evidence of sort of surface weathering. And then we're taking a series of samples, anywhere between say 6 to 12, that are fairly large size, say 50 to 100 grams. And I'll sort of talk a little bit about why we take such large pieces. And you can think of each of those points as one point on the isochron. That's the hope. And so we take these back to the lab, where we then cut the weathered surfaces off, polish it to get rid of the saw marks, and then powder them. Whereas for core sampling, unfortunately, it can be sample limited. You're dealing with something that's 3.5 inches diameter and penetrating basically sort of blind in terms of stratigraphic context in some cases. However, in general, weathering is not an issue. And so the approach is to utilize that vertical interval, fairly short, sort of sub-meter interval. And again, lithology-wise, we're looking for sort of dark, organic-rich, mudstones or organic-rich limestones. And organic-rich, I can talk about in terms of what that actually means quantitatively. And again, we're trying to avoid veining or evidence of mineralization and so on and so forth. So you can see here these 7 rectangles that I've put on this to show the sort of subsamples that we would take from a drill core interval in an attempt to get an age. Okay, so you get your rock out of the field, and the first step that we want to do is an assay to say, okay, are these samples suitable for rhenium osmium geochronology? And in terms of elemental abundance, are they above the cutoff? And so, as I said, the first step is to cut and polish. And so we're taking this kind of hand sample and reducing it down to something that's a little smaller, and it's got rid of the weathered surfaces. And then we use a diamond encrusted polishing pad, an industrial diamond pad, to clean off any metal saw marks, so there's no metal contamination. Then we wrap these samples in sort of thick plastic bags, and then break them into sort of small centimeter scale chips using a rock hammer that's been taped in duct tape. And then we put them into an agate shatter box, a ceramic or agate shatter box that will produce a very fine grained powder. So here's a series of powders here. And so taking that powder, we then do a rhenium test. And what that means is we add a small amount, a known amount of powder, we add a tracer solution, it's our spike, which has a known elemental and isotopic composition of rhenium and osmium. Then we add an acid medium, in this case it's inverse aqua regia. And then we, over the course of a couple of days, digest the sample, mix it with the spike, and then isolate the rhenium cut from the matrix. And so this is these down here are a couple of rhenium, there's 4 rhenium tests here, and in aqua regia, this very bright orange colored liquid. So the next step is to isolate the rhenium cut from the matrix. We do that by a series of chemical steps, isolation of the rhenium, and then we run it through an ICP-MS. At Yale here we have an ICAP TQ for elemental rhenium abundance. And so we have that isotopic, remember this is isotope dilution, so we can then get at the rhenium elemental abundance. And if we're dealing with something that's on the order of 0.5 nanograms per gram or parts per billion or more, then we can proceed forward with full rhenium osmium geochemistry for those samples. If it's under 0.5 ppb, we tend not to push forward with it because the osmium level of osmium in those samples will be really low and produce sort of imprecise data. But in some cases, we go ahead anyway, and sometimes it works out. So if, in your case, we're close to the 0.5, we generally go ahead and try it, but this is somewhat of a cutoff. So I don't get completely inundated. Clean lab chemistry. Okay, so we've got our ceramic shatter box where we've produced these powders. And the next step is Carriage tube digestion. So these are the Carriage tubes here. Hopefully you can see my cursor, my little hand thing. These are borosilicate glass vessels. They're used once. They're pre-cleaned through a series of nitric, aqua regia, and then Milicu. So incredibly low blank chemistry. So we add a known amount of powder. We add a tracer solution again, and then we use hexavalent chromium oxide as our digestion medium. We seal these tubes with a blowtorch, and then we heat the samples up to 220 degrees Celsius for a couple of days. And that allows the spike in the sample to fully equilibrate and sort of produce a homogeneous solution. Then we want to isolate the osmium out from that. So we use solvent extraction, in this case chloroform. Osmium really wants to become wants to be a chloride or bromide or fluoride. So that's its chemical behavior. And then we microdistill it, and that involves a little bit more of the hexavalent chromium, purifying that osmium into a small drop of hydrobromic acid. The rhenium cuts, we isolate that out, and we run it through column chromatography, sort of typical column chromatography that I'm sure many of you are familiar with. So we now have our osmium and our rhenium cuts, which we then analyze using thermal ionization mass spectrometry. And both of these elements ionize as negative ions, so it's negative thermal ionization mass spectrometry. And yeah, so a nod to, so after the 1989 paper, there was a little bit of a lull, a series of analytical papers, including this 2003 paper, where Dave Selby and Rob Creaser did a methodology study looking at dating a series of known age samples with a different range of sort of acid techniques running from hydrofluoric acid, chromium oxide, and aqua regia, and so on and so forth, trying to approach what is the most accurate age. And so this chromium oxide technique allows us to get at a depositional age. So it doesn't fully break down the silicates, and so we're not releasing any osmium within either some of the iron oxides or even in some of the sort of more sort of robust minerals, the plagioclase and biotite, and so on and so forth. So it's not a detrital signal we're getting, instead it's the hydrogenous osmium that's associated with organic matter. And then a nod to some of the other work for the mass spec side of it. And so cosmochemistry and sort of high temperature mantle geochemistry side of the rhenium osmium system had been using a range of techniques trying to sort of give some more life to the rhenium osmium system because of the compatibility variations, which are not seen in things such as lutetium hafnium or samarium neodymium. And then it was these two papers which came out really closely together, two 1991 papers, Rob Creaser and the Volkning paper, So these two papers, what they were able to show was that ionizing osmium as negative ions was far more efficient. And they produced these activator solutions, which are added to the sample on the filament to help liberate and lower the work function, as it were, of these. And so these two papers were real game changers, coupled with the 2003. So that's the sort of expansion, one of the reasons that drove the expansion and proliferation of rhenium osmium, both in the high temperature cosmochemistry and now more recently in the sedimentary realms. Okay, so little dull bullet points here. So rhenium osmium, as I said, measured as negative ions. The rhenium, we take that sample and we load it onto nickel wire filament. And rhenium is measured as 185 rhenium, 187 rhenium, or masses 249, 251. So these are measured on Faraday cups. And then we, for mass fractionation correction, we correct to the known 185, 187 ratio of 0.59738. So this is the filament up here. This is a platinum filament for osmium. And that little crimp in the middle is a flattened surface that we flatten with a set of pliers, and we load our osmium onto that. The magazine here for the mass spec will hold 21 samples. So this is put into here, pumped down under vacuum, and this is the thermal ionization. This is the Triton in my lab that we run. So these are the sort of the steps for generating the isotopic composition data. And so we separate out magazines, one magazine for rhenium and then one for osmium, so there's minimal interference. Osmium, as I said, is loaded onto platinum wire, and osmium 186 through 192 measures trioxides via ion counting on a secondary electron multiplier. Mass fractionation is corrected for using exponential law with this ratio, and then we monitor 185 rhenium to correct for any interference of 187 rhenium on the 187 osmium, because it's a mass spec. It doesn't care what element you're measuring, it just cares about masses. Okay, so that's a little bit about the mass spectrometry and how we generate the data. The next step is data reduction. So we get our rhenium osmium isotopic data, we get our osmium isotopic composition data, and then putting it in through the spreadsheets, which basically strips off the spike, again gets us down to the isotopic composition and elemental composition for our samples. So it's stripping off that spike to give us our unknown. In terms of data reduction, predominantly we've been using Isoplot out of the Berkeley Geochronology Center, which is a macro added onto Excel. More recently, Pina Vermeesh has been working hard on a series of online tools, including Isoplot R, which I've started to use as well. And so it's between these two systems where we're reducing the isotopic data to generate our rhenium osmium isochrons. Okay, so applications. I'm going to move on to some of the uses for rhenium and osmium once we get this isotopic data. So once we get these random numbers generated out of this mysterious box in the corner, what can we do with them and what do they mean? And so I'm going to present the data in the form of an isochron. So for those of you that don't think about isochrons as much as I do, lucky you, but this is a quick reminder. So at the time of deposition, one of the prerequisites for an isochron is that there's a homogeneous osmium isotope composition at the time of deposition. So that's this faint line with the grey spots where it intercepts this axis on the isochron. But these samples have varying rhenium osmium ratios, as illustrated by the range on the x-axis. We have this beta decay of 187 rhenium to 187 osmium. So the line evolves from this flat line to the slope. So this sloped line, the slope of the line is proportional to the age, simple age equation, you should all be familiar with. And so we get an age for isochron, but in addition, we also get the intercept. And this intercept is a back projection to the isotopic composition of seawater, for example, at the time of deposition. So from the isochron, we get two pieces of information. And so this is what it would look like, for example, on the outcrop, is that we have a series of samples taking across a minimal vertical interval on a range of a sort of lateral horizontal bed. Okay, so a case study. So we look at some of the work I've published, a range of collaborators, particularly on Snowball Earth. So I know many of you have seen these papers before, but I just wanted to to provide the context of where all that data comes from and how it sort of fits into the geology, the paleontology, and then of course the geochemistry. Okay, so one of the sort of most sort of well-known in the Proterozoic is the Snowball Earth hypothesis, and this cartoon sketch shows us very sort of low level, or sorry, schematic approach to the drivers behind Snowball Earth and what it looks like, and then how we get out of it. And so the idea, one of the key tenets for Snowball Earth hypothesis is synchronicity or synchroneity, in that if we have a Snowball Earth, it would melt, it would fail, it would melt back synchronously globally, rather than being a series of glacial interglacial cycles. And so testing the Snowball Earth hypothesis requires geochronology data from deglacial successions and deglacial horizons. Okay, so work I did during my postdoc with Francis McDonald. We were working up in the Mackenzie Mountains, and we approached and dated the Twitcher Formation, which overlies the Rapitan, which is equivalent of the Sturtian glaciation. And so we have an onset age of 717, uranium-lead chemical abrasion ID TIMS dates. And from the Twitcher Formation, we have an isochron, which produces an age of 662.4 plus or minus 3.9 million years. And then it has an intercept of 0.54, which tells us something about the isotopic composition of seawater at the time of deposition. Okay, so this was building off of my postdoc with Francis and his group. And we produced a series of ages from globally distinct paleocontinents that showed the Sturtian glacial event lasted for 55 million years. And repeatedly from different locations, the deglaciation was globally synchronous with an uncertainty of the Rooney-Osmium system. And then there was some criticism about potentially the Rooney-Osmium system not being entirely reliable, and people wanted sort of further information and further testing of it. And so the obvious approach was to leverage the uranium-lead system on zircons from post-snowball horizons as well, to sort of back up or test even the Rooney-Osmium system and see perhaps is there something systematically wrong. And I'll show over the next few slides that instead we were supported, and it was confirmed that the glacial epoch lasted this long, and these ages from the Rooney-Osmium system are robust. So we went to South China, where we were able to sample both glacial and post-glacial units. And so here you can see this is the Maranoan glaciation, Doshantou, basal Doshantou, which has an age of 635, uranium lead again. Down here through the Datang Po, and then on the Chang'an Formation in this location, which is equivalent to the Sturtian glaciation. We had the topmost part of this diamictite as a black shale matrix, which you can see here, with a series of ice-rafted debris clasts. And then overlying it is this maximum flooding surface, this transgressive sequence, throughout which there's a series of airfall ash deposits. There's a series of tuffs, which you can see Dan Condon pointing to here with his really enthusiastic, excited face about dating more ashes here. And so we were able to tackle these units, both with the Rooney-Osmium system and the uranium-lead system. We were able to do this separate labs, separate countries, without talking too much to each other, to see what kind of ages the uranium-lead system would see here. And so the Rooney-Osmium geochronology from the uppermost part of the diamictites, published here, is 661.6 plus or minus 3.5 million years, with a really radiogenic osmium isotopic composition, which is what we would expect from a deglacial setting. You're weathering continents after 55 million years. There's going to be very radiogenic rock flour being flushed into the oceans at that time. So the next step was to look at uranium-lead chemical abrasion ID TIMS data from these tuffs and these zircons. And you can see here this compilation figure that the orange bars, these mean weighted ages for uranium-lead, are identical with an uncertainty to the Rooney-Osmium age of 661.6. So stratigraphically, these tuffs are above the diamictite and all agree with an uncertainty 661, 659, 657. Additionally, from other parts of China, there's uranium-lead ages of 659 here. And then from Australia, Mark Schmitz's lab generated ages of 663 from, again, within the topmost part of the diamictite maximum flooding surface. So from several paleocontinents, we can show that the Rooney osmium ages are identical within uncertainty, robust, accurate, and relatively precise, and in agreement with the uranium-lead system. Okay, so moving on to the second component of the applications, leveraging osmium as a paleoweathering proxy. Okay, so folks are probably more familiar with the strontium isotope in carbonates, and here, a compilation figure from the MacArthur figure from the geological timescale 2020. You can see with the Cretaceous, so this Cenozoic strontium curve, where this rapid rise, and there's a lot of work been done on understanding the drivers of that rapid rise, whether it's tectonics or the evolution of seawater chemistry and through other means. And the strontium isotope system has two inputs, and the strontium isotopic composition of seawater on this axis reflects a balance between these two inputs, a continental flux, which is radiogenic, and then a mantle flux, which is unradiogenic. The strontium has a residence time of about 2 to 3 million years. That is, it takes 2 to 3 million years for the ocean to change its isotopic composition. So that reflects, or that is one of the limits on the resolution of strontium isotopes. And so switching a little bit over to osmium, but keeping in mind the approach for strontium, this cartoon here shows the osmium isotope, or the osmium space as a paleoweathering proxy. You have a series of sinks, for example, organic rich sediments, and you have a series of inputs, both from the continents and from the mantle flux. And so putting some numbers on this, some isotopic composition space, the continents are delivering radiogenic osmium. Modern day Lewis has a composition of about 1.4. So it's an average, but as you can imagine, it's related to the compatibility. You can see a huge range in osmium isotopes across lithologies, from Archean gneisses, which can be incredibly radiogenic, values of 3, 4, and even 5, all the way down through to sort of modern basalt, which would be unradiogenic, 0.15, 0.2. And then your mantle flux, so the mid-ocean ridge or basalts, when these are weathering, they're going to be producing and generating a flux of 0.13, so highly unradiogenic. So the osmium system has two really distinct end members, which are contributing to the isotopic composition of seawater. And the osmium isotopic composition of seawater today is 1.06. That's pretty homogeneous throughout the world, and indeed over a depth profile within any ocean basin. So it's very well mixed, and has a residence time on the order of 20 to 50,000 years, depending on the flux calculation, the flux inputs to those calculations. So much higher resolution than strontium. And yeah, the mixing time in the modern oceans on the order of 1,500 years, so much, much shorter. So it should be globally homogeneous, but using a 50,000 year residence time, that's an incredibly powerful tool to leverage for our questions. Yeah, and so you can see the contrast between osmium and strontium, and coupling these two systems on different lithologies is a really powerful approach. Okay, yeah, and so if we're at our outcrop or our drill core and we're sampling and we see a range in osmium isotopic composition, there's a number of reasons for this. For example, this change here from a value of 1 down to 0.3. This could be related to enhanced basaltic weathering, could be more higher paced events such as an impactor in weathering, or it could be something slower such as rifting in a sort of basinal opening. So, using these osmium isotope compositions, we can then start to rule out and interrogate potential events. And as an example, looking at OEE2, so ocean anoxia events and the Sedimentary and Turonian, a couple of studies here from US sections and US cores. So OEE2, positive carbon isotope excursion under global greenhouse, ocean deoxygenation, and large turnovers in marine life. And the osmium isotope from multiple locations shows that there was actually a series of pulses, so multiple fluxes of lip activity associated with large igneous provinces being erupted and weathered. And so you can see this here in osmium isotope space, where you're going from a very homogeneous value of about 1, 1.3, and a rapid decline down to near mantle values, as driven by the enhanced basaltic weathering and this flux of, magmatic osmium, which is going to be really distinct from any continental flux. And so, leveraging the osmium system along with new argon-argon ages here, we were able to show that it was a dynamic and multi-flux, so multi sort of pacing of this lip eruption that drove the LE2. All right, so hopefully I've convinced folks that there's a lot of use for rhenium osmium geochronology, and we're just starting to leverage the osmium isotope system for paleoweathering. And if you contrast, the GTS has a chapter on strontium isotopes, which shows, huge portions of Earth history covered by strontium. The osmium chapter is far more event specific, looking at, for example, the PETM. And so one of the things I'm really interested in is expanding the osmium record across larger portions of the Phanerozoic. But thinking about the isotopic system and thinking about future work, one of those briefly towards the end now, highlight a few avenues that we're working on as a community. So the current limit of precision for rhenium osmium sedimentary rock geochronology is about 0.5%. And that includes when you incorporate 187 rhenium decay constant uncertainty. So when you're comparing argon-argon and uranium-lead ages, you're going to include your decay constant uncertainty, and it's the same with rhenium osmium in any of those ages. And so you would see a second number in the uncertainty, a larger number. And so focusing on this, in 2018, I was working with one of my postdocs, Yang Li, was looking at what's the largest source of uncertainty in a rhenium osmium age. You can see along the bottom here a series of contributions, for example, the weight, the actual mass of your spike, what's the uncertainty on that mass, the isotopic composition of your spike, and then the standard, any variation in the rhenium standard, which is very minimal at this point. And then your blank composition and your blank contribution isotopically and elementally. And then over here in red, looking at half-life. And so this was a modeled approach that if you were able to improve the precision of any of these components by about, say, 15 to 20%, what would be the increment in precision? And so we're ranging from the actual precision here was just under 6.8 million year uncertainty. And so improving the precision by about 15 or 20% on these components showed an uncertainty improvement of about 0.3 million years. And so coupling all of these together, for example, the isotopic composition, the uncertainty, and the isotopic composition of your tracer and the half-life would then add up to a larger improvement on the uncertainty. And so this is something that we're starting to work on. And then the way to get at that decay constant uncertainty is through intercalibration of the rhenium osmium system with uranium lead data. And so there was a paper by Dave Selby in 2007, which produced a decay constant and a decay constant uncertainty that matched what was previously known through calibration with iron meteorites, and that we had a fairly good handle on the decay constant, but the uncertainty was not improved. Unfortunately, this paper, the corresponding uranium lead ages were pre-chemical abrasion IV TIMs. So the obvious thing is to go forward with dating those samples using uranium lead chemical abrasion IV TIMs, all the bells and whistles, and get the highest precision, and then dating those same samples using rhenium osmium. So that's the next step that we're working on. And together, coupled with that, what's required is a tracer solution, which is gravimetrically based. Sorry, yeah, and so this is the paper that is currently right in front of me, and I'm working on it. And as a community, we're coming together to both homogenize and be more transparent in our presentation of data reporting and methodology, as well as generating a new tracer, which is gravimetrically calibrated, i.e. we can trace it back to SI units. And this is something the uranium lead system, the argon-argon system have been ahead of us for too long, to be honest. And so this is work that needs to be done. It's not particularly fascinating or exciting to many of you perhaps, but it's the fundamental step geochronology groups are working on. And so, this is something that we're pushing forward, and we should hopefully be publishing fairly soon and distributing a community-wide reference solution as well as tracer solution to labs worldwide. And yeah, so hopefully I've given a good introduction to the isotopic system and some examples of how this chronometer can yield accurate and relatively precise age constraints, ranging ages from the Archean Paleoproterozoic through into the Paleozoic. So I'm recently working on some Cambrian strata. So where we don't have biostratigraphy, we can produce radiometric ages that can help calibrate and better interrogate Earth history. And then the osmium isotope system is a high resolution, 20, 30,000 year resolution chemostratigraphic tool for investigating interactions between the lithosphere, biogeochemical cycles, and life, and understanding interactions and causation relationships. And with that, I will stop talking, say thank you very much, and I'm happy to take any questions or chat more about some of the issues or the aspects I've talked about.
Great. Well, thank you very much, Alan. I really appreciate that talk. That was super accessible and right on time. So I appreciate it. I'm going to stop the recording now. We can jump on to some questions.